So what we have here are polar equations for various circles and lines in the xy plane, but they're expressed with polar equations. So let's see how that works out. The first one we have here is pretty straightforward. The circle R is equal to capital R. That describes all of the polar points whose R coordinates is fixed. And remember, the R coordinate represents how far away from the origin you are. So if this is the origin here at the middle, all these points that are distance r away from it should belong to this curve. Of course, if they're talking about the set of points an equal distance away from another point, that's of course a circle. It's a circle of radius r. So r is equal to a fixed number gets you a circle. There's other ways to get circles as well. Let me do a chart of theta and r values here really quick. So if we let theta is equal to 0, then cosine of 0 is 1, and we get d. Theta is equal to pi over 2. We plug that into cosine, we get d times 0. Pi, we get negative d. Continue my chart. 3 pi over 2. Plug that into cosine, and we get 0 again. And then 2 pi, of course, is the same as 0. That's d. Let's make sure my d's and my zeros we're able to tell them apart here. All right, what does this mean for us? So let's sketch this on a graph. So here is my xy plane. And I'll plot some of these points. So at theta is equal to 0, so out here on the right, I got d, so we'll go out d. There's the distance d. And then at theta is equal to pi over 2, I get 0, so I don't go out at all. And so what happens is it will decrease from d down to 0 as we rotate from theta is 0 to theta is pi over 2. Okay? Now, what happens between theta is pi over 2 and theta is pi? Well, we are starting at 0 and going to negative d. And I'm assuming d here is positive for my picture, of course. And if we're just going from 0 to d, well, then we will be growing back to d like so. However, or negative d on the xy plane. However, because we're talking about negative values, those get flipped to the other side of the xy plane. Likewise, as we go from, so we went from 0 to negative d between pi over 2 and pi, going from pi to 3 pi over 2, we would decrease to 0, but that just means we're going from the opposite side around like so. Finally, going from 3 pi over 2 to 2 pi, we're going back into the positives. We're starting at 0 and going up to d. And so what we end up having is, ignore this red stuff because that's the stuff that we reflected to the opposite side of the origin. So I'll erase that for us real quick. This stuff never actually happened. And what we end up with is, notice that we actually rotated through it twice. We get 2 rotations of the circle. It has diameter d, because you can see that the center of the circle would be here in the middle at d over 2. Halfway. And we get 2 rotations of it, starting at this point here on the right. So we think of this as it's tangent to the y-axis, hitting it at the origin. And if you don't believe me that this is a circle, you can prove it. What do we have here? We have r is equal to d cosine of theta. I can multiply both sides by an r to get dr cosine of theta. And then r squared becomes x squared plus y squared is equal to d r cosine becomes x. And by completing the square, d squared over 4 plus y squared equals d squared over 4, I get x minus d halves squared plus y squared is equal to d halves squared. And so with a little bit of algebra, you can see that you get the center of the circle at d over 2, comma 0, this point right here, and the radius is half of d. So of course the diameter would be twice half of d, which is just d itself. So that's why it actually is a perfect circle. But if you plot points, you can see that you generally get points in the shape of a circle as well. All right. Very similarly, I'm not going to do all the same work again, but very similarly, we can see that if we do r is equal to d sine of theta, we'll get a very similar picture, but instead of it being tangent to the y-axis, will be tangent to the x-axis. So we start at 0, and then we go around the circle like so, going up here to d, with a center of the circle at d divided by 2. And you can check my work by doing a similar chart of values like we did just a moment ago. All right. The other thing to mention is that I'm assuming that d is positive in both of these pictures. If d was negative, then we would have the negative versions here and there, be reflected to the other side of either the y or the x-axis, respectively. So those are the 4 different types of circles that you see. Most of the time you see this circle centered at the origin, but these circles tangent to the origin are also common as well. Here's a more obvious one. Sort of like the first one we did was pretty obvious. It's just the distance of points away from the origin. If I just fix my theta value to be equal to alpha, I mean, I'm talking about stuff like theta is equal to pi over 6, for instance. Well, what would that look like? Well, I'm just setting an angle of pi over 6. So let's see what that would look like. It's 30 degrees. But also points could have negative radii. So at 30 degrees here, and then 30 degrees in the opposite direction, or 210 degrees if you want to think of it that way. Well, that's the angles that my points are allowed to be in, but my radius could be whatever we want. And so we get all the points going out this direction, as well as all the points going down that direction. Okay. As for the next two, we have r cosine is equal to a and r sine is equal to a. All we really have to do for these is to think, well, what is r cosine? That's x is equal to a. That's why I wrote it right here. And r sine, we can substitute that in for y. And so we get the very basic horizontal and vertical lines. Here we get the vertical line where x is equal to a. And then here we get the horizontal line where x is equal to a. And if you want to see if you believe this, you can always plug in values. You know, for example, let's plug in the value pi over 6 into this equation up here. If I plug in pi over 6 into cosine, well, r is equal to a divided by cosine of theta. So that's going to be a divided by cosine of pi over 6 is root 3 over 2. And that would be 2a over root 3. And if you plug that into a calculator, you could always, let's just say a is equal to 1, for instance. You can see that that would get you this point right here. And if I make a bigger angle, maybe pi over 3, that gets me 1 divided by cosine of pi over 3 is 1/2. That gets me the number 2, or 2a if you're keeping the a in there. And so it's a little bit longer when you do this 90-degree angle. And you can see that you'll actually will get the points on this line going up and down. All right, so let's take a look at a question based on being able to graph these guys. So we want to sketch a particular region. 0 is less than cosecant, is less than or equal to r, is less than or equal to 2. All right, so how would I break this down? Well, first of all, something to note is that helps us out is that we're only dealing with positive values for r because our r is strictly greater than 0. So we don't have to worry about negative r values. So what I could do to solve this is I could take these boundary conditions. The radius has to be bigger than cosecant. So I could take r is equal to cosecant of theta, and I could divide by cosecant to get r over cosecant is 1. But dividing by cosecant, that's the same thing as multiplying by tangent. And we just saw that this is one of those lines. But how do I remember that? Well, I just replaced r sine. That's just the same as the variable y. So what I'm dealing with is just the variable y is equal to 1. I can also take this other boundary condition, r is equal to 2. I wouldn't rewrite this. So if you wanted to, you could rewrite this as square root of x squared plus y squared is 2. X squared plus y squared is equal to 4. But that's just a sillier way of saying it's a circle of radius 2. So I've got the circle of radius 2 and the line y is equal to 1. Let's put those together. So I'll do those in two different colors here. So in blue, I'll do the line, it's the horizontal line y is equal to 1. And in red, I'll do the circle of radius 2. Either way, these are the same thing, right? Circle of radius 2, it's centered at the origin. So I start at the origin and I go out 2 in every direction. Alright, and I need to think of what region am I talking about here? Because it's not clear what's on the inside and what's on the outside. But that's where the fact that we have to deal with a positive radius r. Okay, and that means that we're bigger than the cosecant, and that's where this one came from. Since we're bigger than it, the radii should be bigger, but we're less than or equal to the radius equaling 2, so we should be inside of that, and that's why we shade between the two curves at this position here. We get this top chunk of the circle, and that's the region where all of my r and theta values satisfy this inequality up here on top. Let's take a look at one more type of curve. This is a special type of curve. You don't usually deal with this in terms of x and y coordinates because they're most easily expressed in polar coordinates, and it's called the cardioid. So let's take a look at the cardioid here. And we've got r is equal to 4 minus 4 sine of theta. And you know it's a cardioid if it has one of these two types of equations. Up top here, a plus or minus a cosine, a plus or minus a sine. And when I sketch these cardioids, they're all going to have the same basic shape. They're going to look like a cardioid has the root card, like a cardiovascular. And so we're going to see something that looks sort of like a heart, actually. And to do this, honestly, I just do my theta and r values. So I'm going to do theta values 0, pi over 2, pi, 3 pi over 2, and 2 pi. All right, plug in a 0, 4 minus a 0. Plug in pi over 2, 4 minus 4. Plug in pi, I get 4 minus 0 again. 3 pi over 2, I get 4 minus a negative 4. And then finally plug in the 2 pi, I get 4 minus 0 again. So let's plot all these points here on the xy plane. So at theta is equal to 0, I'm going to go out 4. At theta is equal to pi over 2, I'm going to go down to 0. So in between, it reduces from 4 down to 0. But then you'll notice that after it goes down to 0, it goes back up to 4 as we increase the angle to pi. So here it is at theta is equal to pi, and we're going to increase it back to 4. Then it's going to increase even further to 8, so we'll go down I didn't make my line long enough there, did I? So I need to go twice as far down as what I used to be. So if this is my 4, this is my -4, then this would be -8. And I go twice as far down here, like so. And then I decrease my, excuse me, I made a mistake earlier, didn't I? 4 minus 0 is not 0 by any stretch of the imagination. 4 minus 0 is 4. So I need to reduce this just down to 4. And you can see here that this looks at least vaguely like the shape of a heart. I won't fill it in or anything because unlike the last problem, this is equality, not an inequality. So I'm just looking at the boundary of this heart-shaped region. And that's the usual way. If you ever see this format here, you could prove to yourself if you want how to fill in the dots. I could plug in a pi over 6, for example, get 4 minus 4 times 1/2, and that's 2. So at pi over 6, this angle right here, I should only go out 2. But you can convince yourself that these are indeed how you fill in the in-between spots. Right, so if you all you have to do is just take care of the 4 cardinal directions here: north, south, east, and west, 0, pi over 2, pi, 3 pi over 2, and 2 pi. And once you have those, you can see generally how to fill in the rest of the heart shape if you recognize that you're dealing with a cardioid.